George Boole, an English mathematician. His logic is undeniable. Okay. His logic for logical decision making gave birth to logic gates and logic circuits. Therefore, undeniable. According to George, using a specific set of logic, one can get the desired decision from a pile of data. Pretty deep stuff. Gottfried Wilhelm Leibniz sounded like I was cursing. Anyway, he discovered the binary number system ones and zeros and has described its usefulness. Ones and zeros? Useful? It may sound like a joke, but our whole life is made up of ones and zeros. Combining both George and Gottfried's discovery, we have a set of logic gates today which help mankind make hard or complex decisions by cleverly implementing them in a logic circuit. It also gave birth to research on theorems and how it can be used to simplify a logic circuit. Logic gates. NOT gates. A gate that can only take in one input. NOT gates, also known as an inverter, inverts input values and outputs them. So input a 1, the output would be a 0. AND gates. Outputs a 1 only when all outputs are 1. NAND gates. Similar to the NOR gate, except this gate is a combination of an AND gate and a NOT gate. It has an output of 0 only when all inputs are 1, opposite of an AND gate. The OR gates. As long as one of the output is a 1, the output will be a 1. NOR gates is a combination of an OR gate and a NOT gate. It inverts the output value of an OR gate, so output will only be a 1 when all inputs are 0, a total opposite of the OR gate. XOR gates, also known as the exclusive OR gates. Its output are only 1 when both inputs are on the opposite of each other. XNOR gates, also called the exclusive NOR gates, has an output of 1 only when all inputs are the same value. Traditional logic gates and modern logic gates. What are the difference? Traditional logic gates was initially designed for simpler systems, whereas the modern logic gates was created for a more complex system. They both have the same function, but they are different in design and their symbols. Theorems. When x or complement x, result is 1. When x or x, result is x. When x or 1, then the result is 1. When x or 0, the result is x. When x and complement x, result will be 0. And next, when x and x, result will be x. Next, when x and 1, the result will always be x. When x and 0, then result will always be 0. Following theorems are based on commutative law, where the sequence does not matter. X or Y is equivalence to y or x. Similarly, x and y is equivalent to y and x. And then there's the associative law. Sequence of work does not matter. X or bracket y or z is equivalent to bracket x or y close bracket or z, also equivalent to x or y or z. X bracket yz can be written as bracket xy close bracket z or xyz. X bracket y or z is equivalent to xy or yz. Bracket w or x close bracket open bracket y or z is equivalent to a sum of product wy or wz or xy or xz. X or xy is equivalent to x. And x or complement xy is equivalent to x or y. Complement x or xy is equivalent to complement x or y. The complement of x or y is also equivalent to complement x and complement y. Similarly, the complement of x and y is equivalent to complement of x or complement y.